This is VLSI data conversion circuits, lecture 53. In the last class we were discussing various trade-offs between binary and thermometer coded DACs or decoded DACs, and we saw that when the INL is concerned, it does not really matter whether you binarily decode the digital data and derive the elements of the DAC, or if you thermometer decode and derive the elements, because INL, which is the measure of the deviation of the analog output from the ideal analog output, right, depends only on the total number of elements which are on, okay, and whether the DAC is realized as a binary decoded version or a thermometer decoded version. The total amount of current that is being generated, which depends on the total strength of the elements being on, remains the same, and therefore it makes sense that the INL, the worst case INL, which happens at mid code, is independent of whether you decode it either way. On the other hand, the DNL, which is a measure of the deviation of the step size from the ideal step size, has a huge peak at mid code when you do a binary decoding of the digital data, alright, and the reason for that huge peak is that when you get to the mid code transition of the DAC, that is 0 followed by all 1s to 1 followed by all zeros, ideally the change in the output of the DAC must be simply one step, and unfortunately, as we discussed the last time, this one step is being realized as the difference between two large numbers, and if there is error in each of these large numbers, it is not all surprising that when you take the difference, the mean value of the difference is indeed one step as we want. However, the variance of the step size is very large because the errors in these two large numbers are uncorrelated, okay. And that definitely is not the case in the thermometer decoded version, because to increase the output of the DAC by one step, every time all that we are doing is add one extra element, right, which gives you that one step. So, the variance of the step size is simply the variance of that individual step that we add, and therefore, the DNL performance for the same variance of the individual step size, the variance when you of the DNL for a thermometer decoded version is much smaller than what one can achieve with purely binary decoding. Unfortunately, when you decode the input data into a thermometer code, the complexity of the logic becomes very high, and it is exponentially related to the number of bits, correct, because if you have a 2 to the 5 number of levels, which is a 5-bit converter, converting from a binary to a thermometer code involves 5 input wires and about 32 output wires, right. On the other hand, if you have a 10-bit converter, you have 10 input lines and 1024 output lines. So, you can see that the complexity of the decoding logic grows exponentially, right. And since the complexity of the logic grows exponentially, one can roughly say that the area occupied by the digital decoding portion will also go up exponentially, because complexity wise we mean number of gates, and if you have a larger number of gates, presumably the area required to hold these larger number of gates on an IC will also increase. Therefore, the area is exponentially related to the number of bits. Then we are wondering if there is not a middle path between one extreme where we have binary decoding, which will make the decoder very easy, and the matching requirements on the elements very hard, right. On the other extreme, we have the thermometer decoding, where the decoding becomes very hard and the matching requirements on the elements is quite relaxed. Okay. So, it is clear that if we kind of walk in the middle where we decode part of the input word through a binary decoder and the rest of it through a thermometer decoder, then we most likely achieve complexity of the decoder which is manageable along with relaxed matching requirements on the individual elements of the DAC, right. So, let us continue where we left off. The example we were looking at is this. The RF is simply a resistor which converts voltage to current. This was say Vref, and we had conductances in this fashion. Each of them connected to ground and controlled by a bunch of switches. Now, in the all thermometer case, all these will have identical conductances and you will have roughly 2 to the, if n is the resolution of the DAC in bits, then a full thermometer will have 2 to the n minus 1 elements. For large n, you can approximate this as 2 to the n elements, right. Now, let us say we want only to partially thermometer decode. The input digital word is of the form B0, B1, blah blah blah, Bm, B m plus 1, blah blah blah, Bm. This part is decoded in a thermometer fashion. Whereas, so these are the Bn. These are binary decoded. The last time around we saw why it makes sense to decode the MSBs in a thermometer fashion rather than the LSBs. So, let us now try and figure out what the DNL is for this case. You understand? So, what are the step sizes of the thermometer coded version? Let us assume each LSB is nominally Vref times G. Okay. It should be G times V ref times 2 to the power m. Is that clear? See, this will be LSB times 1, this will be LSB times 2, this will be LSB raised to 2 to the m minus 1, right, which means that the LSB of the most significant portion of the digital word will be 2 to the m. Does it make sense? All right. Now, when do you think you will have the worst case DNL? Pardon?
Bn equals 0, remaining all are ones. Change to
Bm is
Bn or Bm or Bm plus 1? Okay. So, worst case DNL occurs when you have all zeros followed by all ones okay, and one followed by all zeros. All right. So, this is the binary decoded part, and this is the thermometer decoded part. Okay. Let us now try and calculate what this worst case DNL is. The analog output in this case should be G times V ref, which is the step size, multiplied by one plus 2 and so on all the way up to 2 raised to m minus 1, all right, plus the errors involved in each one of these individual conductances, which is E1 plus E2 plus and so on E2 to the m minus 1. Times G times V ref. All right. On the other hand, the analog output here should simply be 2 to the G times V ref times 2 raised to the m plus E of the 2 raised to the m source. All right. Now, can you comment about these errors and these errors, are they correlated or are they not correlated?
They are not, because they are different sets of code sources.
These guys are coming from the binary code decoded version, these guys are coming from the thermometer DAC. So, there should be no correlation between the errors in the thermometer decoded portion and the binary decoded portion, they are coming from different elements. So, the step size therefore will be the difference between the two analog outputs, which will be what is this character? This is 2 to the m minus 1, all right, and therefore, the step size is g times V ref times 1 plus e 2 to the m minus e 1 blah 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 up to e 2 to the m minus 1. All right. So, the sigma DNL when normalized to the step size is simply or the sigma square of the DNL is sigma square of e 2 to the m plus sigma e 1 square and so on plus sigma e 2 to the m minus 1 square. Does make sense? All right. Now, let us recall that sigma E 2 square is what in terms of sigma E 1 square? Is 2 times sigma E 1 square, and please note that sigma E 1 represents the standard deviation of the single current or the single conductance in this particular case, correct, and you make larger G's by simply taking these unit G's and putting them in parallel. If you want 2 G, you put 2 G's in parallel. If you want 1024 G, you take 1024 unit conductances and put them in parallel. So, you can relate the sigma squares of all these elements using is 2 to the m minus 1 times sigma E 1 square, correct. Is this clear? So, therefore, which means sigma DNL square is simply sigma E 1 square plus 2 sigma E 1 square and so on plus 4 sigma E 1 square and so on up to to the y 2 to the m minus 1. This goes all the way from E 1 to E 2 to the m minus 1, and you have this term which is 2 to the m. So, this must be therefore 2 to the m times sigma E 1 square, and this summation is approximately approximately 2 to the m plus 1 sigma E1 square. Okay. Strictly speaking, it is 2 to the m plus 1 minus 1. Okay. So, if you want to be hair splittingly accurate, all right. Please note that m stands for the number of bits being decoded in a binary fashion. Okay. All right. So, one sanity check is to make sure that for m equal to 0, you must get the variance of a single element, which is definitely what you are getting, is not it? Now, to achieve a certain DNL, please note that as designers, we are interested in finding what levels of matching one must have in the unit element, in this case that single conductance G. In other words, we are interested in what we should make sigma E1 in order to achieve a desired sigma DNL, right. That is the design problem. Is this clear? So, the last time around we discussed how one was going to achieve a better sigma E1, right. Let us say you had some element, some conductance G with a sigma E1 which was not, which was way too high. What could you do to improve sigma E1? Pardon? Increase the area, right. So, and finally what did we, how did we conclude? If you want to increase sigma or decrease sigma by a factor of 2, you have to increase sigma by, you have to increase the area by 4. So, in other words, you must bear in mind that sigma E1 square is proportional to 1 by area. All right. So, given a sigma DNL, what will we do? In other words, if sigma DNL is fixed from the specification, then if m is fixed for a given resolution, right, then we need to go and figure out what sigma E1 is, all right. And once we know what sigma E1 is, we can go and figure out how large we need to make the size of the unit conductance in this particular example in order to achieve that sigma E1, all right. We still have not figured out though how one is going to choose m, which is how we segment the DAC. Does this make sense? All right. So, sigma E1 square is proportional to 1 by area. So, that would mean that sigma DNL square is proportional to 2 to the m plus 1 minus 1 times 1 by area, and this 1 by area, okay, this area refers to the area of the unit cell. Does it make sense? Okay. Now, sigma INL on the other hand how does it depend on m? Pardon?
It is independent of M.
Sigma NL is independent of M, but is dependent on area. So, sigma NL square is also dependent on, is proportional to 1 by area. Alright. One important thing to note is that as the degree of segmentation goes on reducing, in other words, as M becomes smaller and smaller or goes to as M becomes larger and larger and goes towards N, which will result in a fully M equal to N is a binary DAC and M equal to 0 is a fully thermometer DAC. As the segmentation becomes 0, in other words, it is a fully binary DAC, we see that the sigma DNL square becomes very large, or equivalently the area of the unit element required to achieve a given sigma DNL becomes 2 to the m plus 1 approximately divided by the desired sigma square. You understand? So, let me put that down here. So, the area desired is proportional to to the m plus 1 minus 1 by sigma DNL square, which is approximately 2 to the m plus 1 by sigma DNL square. On the other hand, the area of the unit element has no relationship with the desired sigma INL square. All right. What are we trying to do now? So, what we are trying to do is to figure out if there is a sweet spot with respect to choosing the degree with which one segments the DAC, right, and what is our objective function? Presumably the objective function is to try and make sure that the DAC occupies as little a space as possible to achieve a given sigma DNL and sigma INL, right. So, as far as the user of the DAC is concerned, he or she does not really care about what you do inside, as long as the specs are met, correct. And as far as DC performance is concerned, the specs would be the sigma DNL and the sigma INL, or in a more practical case, the worst case DNL and the worst case INL, and assuming everything is Gaussian and so on, the worst case DNL and INL can be related to the sigma DNL and sigma INL, right, which means that you can always take the spec from which you can figure out what sigma DNL and what sigma INL you need to hit. Now, given the sigma DNL and sigma INL, I need to figure out what choice of segmentation will result in a DAC with the least amount of area. Why do I even believe that there is an optimum?
No, because the area of the decoder increases when there is more and more thermometer.
Correct.
Whereas when you increase the binary portion, the area of the current sources themselves, they are increasing.
Okay.
So you have
Yeah, so that is quite right. We believe that there will be a sweet spot, because if we choose a completely binary architecture, the area of the current sources becomes very large, right, because as we just saw, the area of the unit element is proportional to 2 to the m plus 1, all right. On the other hand, the area in total is given by is the total area of the unit elements plus the area of the decoder. This is a digital circuit, right. What is the area of the unit elements? How many unit elements are there? In an n bit DAC, how many unit elements will be there? So 2 power n times the area, where this a these two are the same, all right, plus area of the decoder. So, the area of the DAC can be roughly split up as the sum of the analog areas, if you call these unit elements analog, and the digital area, where the digital area is simply the area of the decoding logic, correct. Now, just to make life simple, let us define m by n. M is the number of binarily decoded bits, n is the DAC resolution, so if you want to call 100% segmentation as a fully thermometer DAC, then the percentage segmentation must be defined as hundred times 1 minus m by n, right. So, if m equal to n, you have 0% segmentation, so 0% segmented means it is fully binary, it also means m equals n. 100% segmented means that this is fully thermometer, which means m equal to 0. Does it make sense? Now, let us plot the percentage of segmentation on the x axis. This is 0% and this is 100%. Okay. So, this corresponds to a binary DAC, this corresponds to a thermometer. all right. So, to achieve a given sigma INL, right, let us plot the area of the unit element, which also is the analog area to or within a constant. Please note that for a given resolution, this 2 to the n is a constant. So, the area of the unit element multiplied by some constant number gives you the total analog area. So, to achieve a given INL, right, the degree of segmentation is of no consequence, and therefore, given this, one can go and find this. You understand? All right, because we saw in the last class that it is the sigma INL which is the worst at the, which is the largest at the mid chord, right, depending on whether you do end point INL or if you do best fit, the constant of proportionality will change, but it will roughly be of the form square root of 2 to the, that sigma will be sigma of the unit element times square root of 2 to the n by 2, okay. And depending, as I said last time around, it will depend on whether you do end point or best fit or something, but whether you do I mean if you define it consistently the same way, this is independent of the segmentation. Therefore, regardless of the segmentation, the line, the area required to achieve a given sigma INL remains constant, right. So, let us say, let us for simply for argument's sake say this corresponds to a sigma INL of say I do not know 0.1 LSB. This is just an example. In other words, for in order to achieve a sigma INL of 0.1 LSB, this is the amount of area required for the unit element, which also is equivalent to saying this is the analog area required for all these elements in the DAC, because the analog area is simply the area of unit element multiplied by 2 to the n, correct. Now, what can you say about if I wanted, for instance, a sigma INL of 0.5 LSB, what should happen to this line? The line should go down or go up?
Go down.
If I want sigma INL of what did I say? 0.5 I said, okay, 0.05 LSB is what I meant. So, if I want a sigma INL of 0.05 LSB, the area must go up by a factor of 4. If I want the sigma INL to go down by a further factor of 2, it should go up from this line by a factor of 16, right. So, in other words, a linear decrease in the INL should cause an exponential increase in the area, right. So, if I plot this on the on a log scale, you will keep this way, this you will have equal spacings, right. For example, let me just start off with a more benign. So, let us say this corresponded to sigma INL of say 1 LSB, and this is some area A1. Let us say this is this will correspond to a sigma INL of half LSB. This will correspond to sigma INL of 1/8, 1/16 and so on, right. So, in this case this must be A, this must be 2A1, sorry 4A1, 8A1, 16A1 and so on, right. So, this is a log scale, sorry 1 2 1 by 4 1 by if I divide by, so sorry 16 A1, this must be 64 A1, thank you. All right. Now, let us see what happens to the DNL. Clearly, to achieve a given sigma DNL, the area must be a function of the percentage segmentation, correct. So, for a given sigma DNL, if I had some area needed for a fully thermometer decoded DAC, right. Can you comment on what will happen when I go fully binary? In other words, this represents the area needed for the unit element to achieve a given sigma DNL, all right, when the DAC is fully thermometer decoded. Okay. Now, can you comment on what happens when the same DAC is realized as a fully binary decoded version? What would the area be required be? It will increase, and it will increase exponentially because it is proportional to 2 to the m plus 1 minus 1, which is approximately 2 to the m plus 1, m equal to n when you want a fully binary DAC. So, you can expect the, I am going to now erase off all these lines. Only thing you need to bear in mind is that this is a log scale, correct. Since the y is a log scale, right, and the x is, I mean linear in m, okay, it follows that this line will be a straight line. Okay. Does it make sense? So, this is the area required for a given sigma DN, all right. You understand? Now, the INL area will therefore will be something like this, right. Okay. So, let me write some legends here. all right. Okay. What can you say about the digital area required? The digital area is exponentially dependent on the number of thermometer bits, which means that this is also exponentially proportional to m, okay, which means that how will that look like? It will be a straight line going up, okay. Now you need some area, minimum area for a binary decoder DAC, and let us say this is the digital area required, which is also exponentially proportional to whatever n minus m. M is the number of bits decoded binarily. So, n minus m is the number of bits decoded in a thermometer fashion. The size of the digital logic is proportional to the number of bits decoded in the thermometer fashion, assuming that the binary portion is nothing, right, that part does not take an area. The total area therefore will be the sum of the digital area and the analog area, okay. So, if this was the sigma INL spec, all right, if we did a completely binary coded design, we see that the amount of area required will be huge, because the analog area occupied by all the cells will be very, very large, right. The digital stuff contributes nothing, and we see that we are now way over designed from the viewpoint of INL. Why? For desired INL, sigma INL, this is all the area you need. This is all the area you need to achieve the desired sigma INL. However, we have that area for the unit cell, and the reason why we needed to have that much of an area for the unit cell was because we needed to hit the sigma DNL. Is this clear? Okay. All right. Then we say, okay, I am going to start segmenting, and as I keep moving from here to the right, we see that the area needed to achieve the sigma DNL keeps reducing, right. At some point it will intersect the area needed to achieve the given sigma INL, all right. And if I attempt to segment it further, what happens? The sigma DNL reduces, but the you will, if I chose this area for instance, I am okay as far as sigma DNL is concerned. However, sigma INL becomes a problem. So, what should I do? I should not fall below the red line. So, what I would do would be to keep increasing the segmentation until I hit the sigma INL line, and beyond that the total area is basically this plus the digital area which is going up exponentially. Please realize that this is a, this is a log scale, right. So, there is a gentle maximum, if you look at the total area, it is probably something like that, alright. And this line, the position of this line depends on details of the technology and such, alright, because if within quotes the logic is, let us assume that is very, very small, then this line will move parallelly down, which means that basically if the logic is very, very small, it means that the decoding is free, in which case you would do, if the decoding logic was magically, it was possible to make it 0 area, then what kind of segmentation would you choose? Then you would choose 100% thermometer, right. So, the relative position of this line is a function of process and so on, and feature size and this kind of stuff, but you can see that for a given technology you will be able to find a sweet spot. Around here there is hardly any difference between whatever degree of segmentation you choose, because this is exponentially falling down, correct. So, even though it is true that the area here is slightly greater than the area here, that difference will be only very, very small, but the difference in performance will be, performance here versus performance here, can you comment? At A and B the INL is the same, but the degree of segmentation is higher at B than in A. So, what can you say about the performance at B? The sigma DNL is clearly much smaller than the sigma DNL at A, alright. So, it seems it makes more sense to choose the more segmented solution, right. So, this is a optimal point of segment. Does it make sense? Is clear? All right. So, we will